Hey, good morning, everybody. I'm Javier Moreno, I'm the director of Sydney. And today is a real pleasure to be able to present the speaker to this seminar, who is Miquel Aguirre. Miquel, probably I met Miquel quite a long time ago. I think I was checking my files earlier on. I met Miquel in 2010 when Miquel was applying for as a PhD student at an early stage research as part of a European project that we had in Swansea in collaboration with UPC and in collaboration with Nantes and collaboration with Munich and other people. I think it was called ADCOM.
ADCOM, yes. ADCOM, yes.
That's right. So we can apply for to be a PhD student in that program. And I remember we interviewed Miquel and 3 or 4 other candidates. And fortunately for us, we chose Miquel as the PhD student. And then he did his PhD with myself and with Antonio here in Swansea. I think we did quite a lot of very interesting research. We have a few papers that are very well cited. We wanted Miquel to stay in Swansea as a postdoc, but Miquel was very keen to work in the area of computational biomechanics. And there is a very well-known professor, Alberto Figueroa, who was either in London or in Michigan. I don't know whether he was in one or the other. Michigan. Yeah. He had already left London to go to Michigan, and Miquel was very keen to work within the area of biomechanics. We were very sad to see Miquel go, but I know that he moved on and did a fantastic career. And I'm absolutely delighted. He then went on to Saint Etienne in France, but I'm delighted that Miquel has decided to come back to UPC and to collaborate with Sydney. So we're all delighted to have Miquel back here in Barcelona, in Lacan, in the UPC, and also working with Sydney. And I know that Miquel's continued to work in the area of computational biomechanics, and I really look forward to hear what you have to present today. So over to you.
Thank you very much, Javier, for the introduction. And yes, I have very good memories of Swansea, and you never know, but we ended up working together again. We haven't collaborated with research so far, but
I'm sure
with other aspects, yes, already, yes. So thank you very much, everyone. So so today I want to talk about the research, an ongoing project that project just started, one ongoing, and then explain what I've been doing also with, as an excuse, explain also what I've been doing in the last years, in the last 5 years. So the project, everything revolves around stroke. And basically I'll explain 2 projects, one on decision support for thrombectomy, which is one of the procedures that also Berko knows very well for the treatment of stroke. And a second project on improving the diagnostics, so accelerating the diagnostics of stroke. So just an introduction. So acute ischemic stroke is a major health problem. So it happens when a clot, a blood clot, blocks the brain artery, and when that happens, there are regions of the brain that don't receive blood supply, so that can lead to tissue infarction. It's the second cause of death worldwide and a major cause of disability. And something very important, it needs to be treated the first 6 hours after the onset of the symptoms. So already with this, you can think that there is a need of very fast decision making, typically with very scarce information. So treatment, we have 2 main treatments, sometimes combined, and typically, but of course, there are always exceptions. For small occlusions, meaning small clots blocking small brain arteries, what they use is drugs, so thrombolysis, which aims to dissolve the clot. For large occlusions, what they use is this technique, endovascular thrombectomy, that has really improved in the last 10 years. And it's basically, the idea is to navigate a stent, which is a device, a metallic device, wired, that aims to trap the clot within its structure, and then the surgeon can pull the clot from the body of the patient. Very important, nowadays 50% of the patients get incomplete recanalization, meaning that the blood supply hasn't been fully restored. And this is either due to being late at the hospital or a suboptimal treatment or sometimes poor surgical planning. So let's go to the first part, the first project, with this decision support for EVT. So this is a project that just recently started thanks to funding from the Ministry of Science here in Spain, and where actually Alberto Aguirre is a new postdoc that just started working on this. So basically, when they plan, so EVT, endovascular thrombectomy, what they want to achieve is a complete recanalization of this patient. This is measured with this scale that you see here. It's called NTC. It goes from 0 to 3. Being 3, the maximum recanalization. So what they want to achieve is this NTC3 for each patient. But also, very important, they want to achieve it in the first try. They call it passes. So in the first pass, meaning that if they achieve NTC3 in 2 or 3 passes, then they know that the possibilities of recovery of the patient lower. So they want to achieve first pass NTC3 for the majority of the patients. Something important is that for this type of procedure, they cannot make patient-specific devices. So they use devices that are already available in the operating room. So something that they have already stored in the operating room. And nowadays, the decisions are mostly based on geometry. So they look at the caliber of the artery, the length of the artery, and based on that, they pick a stent. So they are disregarding all the mechanical phenomena that is taking place. And here we think that decision support tools based on mechanics can really. So nowadays, in the literature, you can find lots of decision support tools, but they are based on medical imaging data. So they try to find relationships between preoperative medical imaging data and the output of the intervention without taking into account this mechanical phenomena. So our aim is to develop an interpretable, I'll explain that now, mechanics-based decision support tool able to answer, given a patient X and a procedural plan Y, what is the probability of achieving first pass NTC3. Interpretable, that's an important aspect of these tools, is because black box machine learning models, there's been a lot of development of that, but at the end, they are not used widely in clinical settings because doctors want to know the relationship between the prediction and how this prediction has been made, especially in cases where the prediction fails. Okay, so this is what we want to achieve, the proof of concept. So taking preoperative imaging data that we may parameterize, taking a stent that we also may parameterize, training a machine learning model, in this case would be a decision tree that is interpretable, able to achieve this, so able to predict the probability of first pass NTC. And here we need to really define a scope because this is very ambitious. There is a lot of phenomena going on. So there is structural mechanics phenomena. There is also blood flow. There are many factors that have an influence on that, like the material properties of the thrombus, the vessel, etc. So we restrict the research to develop numerical tools. So it's really on the development of numerical tools. Also, we won't carry a clinical study in this project. For a first proof of concept, we'll just focus on solid mechanics phenomena that is known, that is the one that governs the most the success of this intervention. And we want to see the influence of the patient geometry and the type of stent on the mechanics of this. So two objectives. The first one is the development of a high fidelity solver of this endovascular thrombectomy based in work that we have been doing in the last 5 years. And the second one, training an interpretable machine learning model able to predict the disease possibility of first pass NTC3. So here there are different aspects, so different circles in green, orange, and red. Green meaning things that have already been developed previously. Orange, things that have been developed but need further development in this project. And red, things that will be developed in this project solely. So the first one, stent deployment. This is something I have been working in the last 5 years. So today, there is a lot of endovascular modeling, if you see the literature, mostly based on commercial software. And when I landed in this group, they asked me, and in Saint Etienne, if we could start a line of research of developing an in-house open source software for stent deployment modeling. So commercial software is very powerful, but it has limitations also. It's not many times not optimized for a specific task at hand. So Abacus or ANSYS can be used for doing crash simulation tests and stent deployment, both things being very different. It's sometimes difficult or sometimes impossible to add new physics, and there is no access to quantities needed, for example, when we use reduced error modeling. So this motivated this development of this open source FEM solver. And the initial scope of this was simulating just the deployment of flow diverters in the brain. That means just a stent that is deployed in the brain, in an artery in the brain, to see if it can cover an aneurysm region. So there is no thrombus, there was no such complexity in this. So this is something I started, and then was continued very successfully by our PhD student, Beatrice Bisichini, funded also by a Marie Curie project that defended last Friday. So when we started, we thought there were two things to do. So first, look for the best strategy to model this problem of a stent of contact of a stent against an artery. Okay, so we thought, well, there are three ingredients. There is the modeling the stent itself, there is the contact against the arterial wall, and there is the computing the contact. So we started with a rigid wall and finding a formulation that was very efficient, modeling stents and the contact. And once this was in place, the idea was in the future to implement this into an efficient programming language, which was done, by the way, by Beatrice. So what we decided to use was a co-rotational formulation. So stents are made of beams. And looking at different beam formulations, we thought that rotational formulations were very efficient. So basically, you can model large deformation of beams. So you have a beam initially undeformed that goes to a deformed configuration. And what they do in rotational formulations is to capture the large display, so to decompose the large deformations of the beam in large displacement and rotations in a moving reference frame, and then the small strains within this moving reference frame. So this allows for using linear elasticity in this moving frame, and it reduces the computational cost. So we adapted this to take into account contact against rigid surfaces. So we added contact terms that we linearized, including rotations, etc. So this was quite a substantial amount of work, and we used an HHT alpha method for time integration. So this is a fully implicit dynamics finite element solver for beam to surface contact. So for the contact search, typically in contact, what you do is a search. So you have a contact of an element against a triangulated surface. There is a search involved, and this is expensive, computation expensive. So we decided instead to use sign distance fields, as they are used sometimes in computer graphics. So you have sign distance field is basically an implicit representation of the surface in a voxel grid, where each node of the voxel grid has information on what is the distance to that surface. Positive outside, negative inside the surface. And it has nice properties, as the gradient, for example, is the normal to that surface. So we wanted to use that in order to have the value of that distance in a specific Gauss point needed in the integration of the contact forces for a beam. What we use in these interpolations, so actually this comes from a paper of Aguirre and colleagues on immersed FSI. So it's a high order kernels used in immersed FSI to interpolate this distance. So we implemented that, and then we validated with several benchmarks. So this is a very challenging benchmark. It's a 2D problem where you have a beam that has an initial velocity and it impacts against two end stops, which are here sign distance fields. And here we have literature results compared to against our problem. We also did this standard test, which is a ring against a surface. So this is just to see the dissipative, or if you have a better time integrator, the energy conserving properties of your time integrator. But in our case, we just wanted to see that it was dissipative. So, so this is the total energy, and we see a decay of the total energy as time advances. And this decay is even larger when you have friction. And then we did a couple of our own benchmarks to see a couple of things that we wanted to check. One was the influence of the voxel size in this contact algorithm. So what we observed is that up to a mid-refinement is sufficient to capture the dynamics of this beam, and it also was very interesting to see that the penetration is typically smaller than the voxel size, so the penetration that we have. And a second test that we did, we wanted to test for a more challenging problem, so we used this Stanford Dragon and net, falling on top of it, and we wanted to observe how many points in those beams ended up having an interpretation which was right. So with that, we were satisfied. And this is the point where Beatrice joined the group, and we decided here to take this code that was originally in Malapa, implemented in a more efficient language, and then add all the capabilities to do a stent modeling, to take patient geometries, etc. So to that, we picked Juliet, which was a programming language that I didn't know back then, but we're very happy with it. So it's nice because the syntax is easy, so it's quite similar to MATLAB, but it's efficient. And then there are lots of packages developed for inverting matrices and other things needed in finance. So Beatrice implemented this there and ended up creating this package that we call endobeams, and now I'm going to show some results. So first thing we did is to benchmark this against the commercial software. So this is, back in the day, this has been further optimized, but back in the day, for simulations were already faster than outputs in a desktop computer. Something interesting for signed distance field that Beatrice has explored a lot is the fact that when you take patient geometries coming from imaging data, what you need to do is segment those geometries, so meaning isolating the lumen area that you want to mesh. So if you use typical finite element meshes, you isolate this area and you end up doing some triangulation and then running your finite element there. But in our case, the segmentation involves the creation of this level set, and we can't stop it there. So we can use directly this level set, which was you need to, they will pre-initialize to make it a signed distance field. That is quite a trivial. So then Beatrice worked a lot on stent modeling. She has many models, but this here I just want to show how he did the deployment. So typically you have a stent that in the reality it's stripped. It has to be navigated to the artery and then deployed. But here we did some simplification, which was doing a half crimping, let's say, and placing the stent in the center line of the artery. So this is the geometry. So the one that you see at the end of this animation is the final geometry before deployment, and here is when the deployment takes place. So Beatrice was just interested in what is the final position of this stent with respect to this aneurysm, and such approach was sufficient in this case. We also did experimental validation. So this is a test that we did in-house. So we got some from medical doctors stents, and this is a 3-point bending test, which this is the recording of the test. So basically, you have this device that pushes the stent downwards, and what we compare is the displacement here against the force measured in this. And we compare the results with our software endobeams and in silico with outputs. So here are the results of the force against displacement curves, which match quite well, both endobeams and abacus against experimental data. And these are the final geometry. Oh, sorry, this is so the final geometry against the experimental geometry. Then the experimental validation continued. So we 3D printed 2 idealized arteries, carotid bifurcation and a stenotic vessel. And a doctor came to deploy using their tools the stent inside. So these are the results of the deployment of such a stent. So what you have is the comparison between the experimental results and endobeams, and you can see that there is quite a good match, with the worst being this result here near the carotid bifurcation. But here we observe there is a large influence on. So here, as a model for the deployment, so in silico, we used the geometry that we input for the 3D printer. But the actual output of the 3D printer, it's a bit different from that input of the 3D printer. So this wasn't taken into account, and this is something that we are thinking now on correcting using scans of the 3D printed geometry. Okay, so something else that we work is in patient parameterization. So in this case, Beatrice used a clinical database, and then from that she did a reconstruction of the main artery, so disregarding the aneurysm. And from this, what we wanted to observe is if we could parameterize such segment, arterial segment, with a few parameters. Because at the end, if we need to train a machine learning model, we need a few number of parameters. So what Beatrice chose is to use a center line, so and discretize this arterial segment using the coordinates of the center line points and the radii at these points. Then we used PCA to reduce the complexity of this parametrization. And then she used that to create synthetic models. So this is still work in progress, but we have some results showing, for example, that the compactness curve, so how many modes do we need to represent the variance, the variability of the geometry that we have. And we observed that with 11 modes is sufficient to represent 95% of the variability of the geometry. And finally, we worked also in surrogate models. So in this case, we use non-intrusive surrogate model. So here, there is no physics, okay? So we just do reduction of the problem. So in an offline stage, what we create is a large number of simulations, snapshots. This is then reduced using proper orthogonal decomposition. And then we train on machine learning a regression model, the relationship between the input parameters and the solution in the reduced space. And online, what we do is to query the machine learning model for a new set of parameters, new star, and then we can always project the solution back to the high fidelity, so to the higher space. So these are the results for one geometry. And here what we are seeing is the average prediction error. So for different size of database, and we can see that as we increase the size of the database, the prediction error is reduced. And what we were interested is in comparing the prediction error against the resolution of typical imaging equipment used in the operating room. So we are well below computed tomography and geography, which was one type of equipment used, but digital subtraction and geography, which is the one used as they operate. So something that they use to get online. So live from time to time, the update of the geometry of the patient, we don't get quite there. So there is still improvement to be done. And ideally, we would like to go towards the resolution of this 3D rotational and geography, which it's more a state-of-the-art imaging tool. And then we did a proof of concept of something just with idealized geometries, but something that we thought was interesting. So imagine this case when we are doing a stent deployment in this idealized vessel. We want to cover this aneurysm. We may sometimes get in cases like this where we don't fully cover the aneurysm. And depending on the size of the aneurysm, you may have even the stent getting inside the aneurysm, depending on how poorly you do deployment. So we thought that it wasn't interesting to do regression on these cases because at the end, we just want to know if we fully cover the aneurysm region or not, but we are not interested in what is the final configuration of a case where the stent goes inside. So we thought it would be interesting to do a classification of failure, non-failure before using our regression model. And this is what is explained in this diagram. And the idea is that at the end, the regression model is only trained for those cases that have been successful and fully covered the aneurysms. So online, once you have a new patient, the idea would be to first query the classification model, know if that position proposed by the doctor would cover the aneurysm sac. If that's the case, then using the regression model to predict the final configuration. So that classification model, of course, for this simplified geometry worked quite well. So this is what they call the confusion matrix of so 0 being failure, 1 being success. So they predicted against the true values. So well, we tested different type of classification techniques, and they work. So finally, the vessel wall interaction. So this is something that I did before, but we thought so. So I did before when I was doing the postdoc at the University of Michigan, and it's something that we have continued doing with my colleague Nitesh Namma, and now he's at the University of Nebraska. And here, well, when we got there, we had to. So it's basically this framework that is called Crimson. It's used for blood flow simulation in the human body. And it's a very nice environment because it takes imaging data, you can segment it, and you can create specific boundary conditions, use all this as input to carry out blood flow simulations. So back on the date when we arrived there, there was a linear elastic FSI solver. So it basically was solving the Navier-Stokes equations with an embedded linear membrane on the boundary. which work very well in general because in the main arteries, let's say, because arteries are highly pressurized vessels that form very little between systole and diastole. So you can assume that this is linear elasticity. But there are other regions of the vasculature where you have large deformations, as for example, the connection between the ascending thoracic aorta, the ascending thoracic aorta and the heart. So you have large displacements and rotations. So there was a need of implementing a nonlinear FSI solver, which is quite a story that I won't explain now. But what we did, we pick is an ALE solver, an ALE technique. So basically, we wanted to capture the FSI phenomena of large deformations in a vessel. And here we had the need of using a total Lagrangian description of the vessel. So here we tested many things. The first thing we used was a membrane, a nonlinear membrane, which worked well until we realized that near the bifurcation regions started to fail. So we needed something else, and we chose to use a shelf. So for shelf, we tested also different things, and we were quite restricted in the fact that Crimson uses a tetraeder for the flow. So basically, for the wall of the flow domain, we need triangles. We also wanted to just use displacement degrees of freedom. So at the end, one of the best options we found, which worked very well, is this formulation proposed by Oñate and colleagues, which is a rotation-free shell formulation. So here we use basically in each shells, what you need is to compute the curvature, which is needed in the sample stiffness matrix. And to get this information on the curvature, use a patch that uses information on the displacement surrounding a specific central element to compute such curvature. So we adapted this, we added the necessary boundary conditions, we added the pore fiber model, even a pre-stressing algorithm to be able to predict what is the state of pre-stress in vivo. So typically you have imaging from the patient, which you have a geometry, but you know that this geometry is in equilibrium with the internal pressure. So we implemented an inverse algorithm to predict what is the state of stress. And then we validated this with some known benchmarks. So this is an axisymmetric test that they call inflation extension. There is a 0D result, 1D result, and there is also experimental results that we used. This is the pre-stressing algorithm. So here we saw the influence of using the pre-stress or neglecting the pre-stress even in the flow solver. So of course, when you sorry, I need to refresh that. Yeah, so with pre-stress, so without pre-stress, you predict lower values of the pressure for the blood flow. So this is some validation against geometries obtained from mice in the lab of Jay Humphrey. And finally, we are observing the influence of the external tissue support. So you have arteries that are not floating in space; they are surrounded by tissue, and we wanted to add the effect of this surrounding tissue. So we added external tissue support, and here we are comparing the results of using or not using this external tissue support, and you had very unrealistic results when you. By the way, in many cases, it's important. So yes. This is a bit what's the background work, and now there is work to do in this upcoming year. So, by the way, now that this shell model was implemented in Fortran, but now we passed with Nitesh everything into Julia. So we have a standalone code in Julia of this shell model that takes Crimson pre-processing input from Crimson and from Vascular. And we would like to couple this with the BIM. So we would like to do a BIM to shell implicit algorithm. So this is the first task that we want to do. Then we want to also capture the interaction of the thrombus against the stent and vessel wall. And then there is also work to do in further parameterization, more accurate reducer modeling, and then finally training of these decisions. Okay, I don't know how much time they have left. Still good? Okay. So that's I'm going into a second project. So it's this data-driven screening tool for acute ischemic stroke. So to explain this, it's good to understand how it is done now and what the limitations of the current pathway for the diagnostic and treatment. So the current pathway is called this drip and ship. So basically, first thing it's so important to keep in mind is that the patient needs to be treated 6 hours after the onset of the symptoms. So you imagine a patient that has symptoms at time T0. Patients typically take some time to realize they're having a stroke. So imagine that after 2 hours, this patient is being transferred into a hospital setting. So it's very likely that if they detect that you're having a stroke, you're going to be transferred in a primary stroke center, meaning a center where they can do further diagnosis and they can do thrombolysis, so they can do drug treatment, but they cannot do thrombectomy, okay, because there are less centers like this. So you are admitted here, times 0+3, for example. Then they do a first CT scan to understand if there are regions of the brain where there is no blood supply. And this is a way to say, well, yes, there is a stroke. And then they do angiography. So this is another type of scan where they inject contrast agent. And with this scan, they can understand if this is occluding a small or large vessel and when. Okay. So in case this is the screening itself. So in case it's a small vessel, they just do thrombolysis. In case it's a large vessel, if you were transferred in a primary stroke center, you need to be. So if you were admitted in a primary stroke center, you need to be transferred in a comprehensive stroke center where they can do thrombectomy. So everything adds up, and this is just, it's quite a realistic timing. So it's very likely that the procedure starts later. Okay. Sorry. So yeah, this late screening risks the recanalization beyond the 6 hours time window. And just for you to know, I just Googled that yesterday. So this is Catalonia. These are the comprehensive stroke centers, mostly all located in the Barcelona area. Blue, in green, the primary stroke centers, and the other ones are just remote centers where they can do remote diagnostics. So imagine living in Lleida, in the Pyrenees, and so on. You can even be farther away than these 6 hours. Okay, so they want, so there's this idealization, let's say, of moving this paradigm in this mothership pathway, where you move the screening in the pre-hospital phase. Okay, so the patient, before being admitted in any hospital, is screened to understand if he's having a large or a small vessel. So if we do that, then the transfer into a comprehensive stroke center can be done way before, and then hopefully you get your thrombectomy done before the 6 hour time. So the objective long-term will be to develop a fast screening tool based on pre-hospital patient data. And there are some requirements. It needs to be fast. You need to use and take a decision fast. And then it needs to be accurate. So accurate, both avoiding false positives and false negatives, because all these add delays in this diagnostics. The data needs to be measured by portable devices operated by paramedics, because we are in a pre-hospital setting. And nowadays, if you look at the literature, there are some things done using physiological data, biomarkers, and even, for example, built-in CT scans in ambulances. But this again adds, so this wouldn't be feasible for its widespread use. Okay, so we're looking for something cheap. So the question here is, could we use blood flow waveforms to do this diagnostic? So something easy to measure with Doppler ultrasound is the carotid artery blood velocity. Okay? So we wanted to see is that by measuring the carotid artery blood velocity, we could detect and locate the stroke. Okay? So this is an inverse problem that I thought also looked very similar to what's done in structural health monitoring. So in structural health monitoring, you have vibrations measured in the bridge, and they want to know if there is damage in the bridge and locate this damage, and sometimes even quantify it. Okay, so there's a similarity here. And our scope will be just to carry out a pure in silico analysis to understand the feasibility of this. So to do this, we wanted to create a data set of patients, in silico data set of patients, of stroke patients. And we use this solver, Nectar 1D, which is a discontinuous galerkin that solves the 1D blood flow equation. So these are Navier-Stokes equations in a deformable tube in 1D, which is developed by Jordi Alaustré, who's collaborating in this project in King's College. So what we would do is to create an idealized patient geometry, an idealized circle of Willis, where we would place at some point a blocking thrombus. Okay, so in general, you can take this as a black box that provides waveforms. Okay, so it can be both pressure and velocity as a function of the patient geometry, the measurement location. So imagine is this one here, the time where you want to do this measurement, the inflow waveform, and then the boundary conditions. That here we use Miquel 3D Miquel boundary conditions, which are lamp parameter models typically used in blood flow analysis. And then, of course, it's also as a function of the location of these reflective boundary conditions. So in our case, we assume that the reflection boundary conditions are just a function of the occlusion site. Okay, so there are no other reflective boundary conditions. And then in our case, we want to do measurements on the left and right common carotid artery. So we can write it as this. So the measurements, waveforms on the left and right common carotid artery are a function of patient geometry, inflow, and then boundary conditions. So based on this, we want to create a synthetic database to find this relationship. What is the, so if we can predict the occlusion location from this waveforms. So there are several assumptions that we did. So first one is that we're going just to use adult physiology. We are going to use the most typical topology seen in this circle of Willis. So there are several variations, but we pick one, the most typical one. We assume no change of length amongst patients, so the skull size doesn't change that much among adults, and also important that the length of the artery doesn't have that much of influence in the waveform. But this, of course, would be a data in the future. And then something that has a lot of influence on the waveform is the radii of the arteries, and this we assume it changes with patient age. So based on this, we can think that the patient geometry is just a function of patient age. Then, based on literature data, we use different flow inflow waveforms as a function of age. So this is known that varies according to age. We use allometric scaling laws to adapt the Winckel parameters at the outlets as a function of the radii. And the radii, again, is a function of age. And then we're going to use different ages between 20 and 80 years. So at the end, we can write our waveforms on left and right as a function of patient age, some random variations that we're going to do, the occlusion and noise that we add in the data. So we tested different options here, and we ended up finding out that the best option is to separate this classification in two steps. One first step where we do a broad region detection. So we created 9 labels that contain the typical regions where a clot might be in ischemic stroke, and then an additional label for the healthy patient. And we want to find to see if we can predict those labels by comparing the waveforms that can be either pressure or velocity on the left and right common carotid artery. So subtle differences between these waveforms may bring information on where this broad region is. And then once we have detected this, we use a second classifier to detect the bifurcation generation within a specific broad region. So for example, we have detected this broad region here, that is the middle cerebral artery. We may then detect if we have a medium vessel occlusion or a small vessel occlusion, which is valuable information for the screen. So to do that, we are not going to compare waveforms on the left and right, but we're going to compare given that we have used the first classifier, we know if the clot is located on the left or right hemisphere. And we are going to compare a waveform against its healthy counterpart. And by doing this comparison, we can then predict this bifurcation generation. So this is the overall framework. Sorry, it's a bit messy, but we create the database. We have the 2 classifiers. And then online, what we would do is to first get these waveforms on the left and right, and then predict this broad region. If it's a healthy patient, stop. If it's unhealthy, what we want to predict is the measured waveform on on the specific site against the healthy one counterpart. So we need a healthy counterpart. And to do that, we created a reduced order model to predict the such healthy counterpart in real time, because this would be. So these are some of the results. So this is for the classifier 1. So here we use different number of training samples. I wanted to see how our F1 score. So F1 score is a score that takes into account both the recall and the precision. So the recall is to avoid false negatives, the precision is to avoid false positives. So in short, if you have a high F1 score close to 1, that means that you have an algorithm that has a small number of false positive and false negatives. So here we wanted to see which combinations of waveforms work better. So we use just pressure, just velocity, and velocity and pressure. So just pressure does a very poor prediction. Just velocity does a good prediction, and adding pressure doesn't add a lot of accuracy. So we decided to, from now on, just use velocity waveforms. And then we also wanted to understand the influence on the noise level. So we always test the results with noisy data. What we wanted to see, which sounds obvious, but at least we wanted to find out if so to have a confirmation, if training with or without random noise improves the solution, and it does improve the solution. So these are the confusion matrices of this first classifier for the different labels that we created, these 9 labels, so 8 regions and healthy. Of course, no noise, both in the training and the testing, is the best. Training with no noise and testing with noise, it's really a poor choice. And then something closer to reality, training and testing with noise. We get a good balance. Yeah, sorry, this was already in the other. Okay, so this is for the second classifier. So once we have predicted a given region, so for example, this region here, the middle cerebral artery, to understand if it's a small or a medium vessel occlusion. And again, we do compare the 3 scenarios: no noise, training without noise, and testing with noise, and then using noise in both training and testing. And for these idealized cases, we still get very, very good results. And finally, this is the overall framework. So here, what we try to summarize is the influence. So these are for different noise levels, so from 0 up to 20 on the training. So we want to see is how good we predict the. So here we get wrong region, wrong bifurcation generation. This is true region, true bifurcation generation. So we would like to get as much as cases so very close to 100% in true region and true bifurcation generation. So when the noise level is quite high, it's true that our prediction in some of the region decays quite a lot. So we think that is due to the fact that we are using these idealized geometries, and we think that by considering asymmetries and other topologies, we could improve this prediction. So just conclusion. So we implemented endovins with this efficient finite element solver for vein-to-surface contact, including the validation against experimental data. We did a proof of concept of parameterization of geometries and reduced order modeling. And for AS diagnostics, we did a synthetic proof of concept using idealized circular fluids. So future work for this project 1, we want to include the femoral wall, the thrombus interaction, a validation of the thrombectomy procedure, either using literature data or clinical data. And then also we need to do this training of decision tree. And then for the project 2, we'd like to see the influence of different anatomical variations, the use of non-idealized geometries, of material properties that were not included here, so changing material properties of the patient. And then, of course, this would need clinical data to be validated. So that's all. Thank you for your attention.
Thank you very much, Miquel, for the presentation. seminar lecture. You've got that. Thank you also for sticking to time. Thank you.
Oh, you did?
Your timekeeping has been absolutely fantastic.
Okay.
So we've got ample time for questions. We've got quite a large audience. So please, questions.
So very impressive. And I have one question about wider. So why you're using AHT for the endocrines and all that? So assuming dynamics, but it looks pretty like pseudostatics. And
Yeah. So
I'm wondering whether you use dynamics for regularizing the problem. It's really you need dynamics, inertial forces, because then you have one solution.
no, we want to have a very complete solver having everything, and then actually for the problem that Beatrice was solving, we use damping. So we use viscous damping to get to this final config. So we are interested in the static solution, the static solution at the end.
So inertial forces.
Yeah, that's enough. That's enough. Yeah, but yeah, it's a dynamic solver that we don't exploit so far. But maybe from thrombectomy that would be more because you're interested in the dynamics there.
You had the second
Yes,
question.
yeah, related to the what you mentioned that the reduce of the method so works fine as far as you things work on the general direction, but if something else happens, then you reduce all the method. I'd like to know what your experience, or if you can include these other scenarios in your reduce all the method may help. Or
Sorry, but it works fine in so I didn't get the first one.
when it was the stand that was going into the
Yeah.
out of then say the reduce, then you were not so happy with the results.
Yeah. So basically what we wanted to do there is to exclude from the training so we're not interested in when the stent goes inside the aneurysm. It's something. So we want to know if it will go inside. That's an information to give to the surgeon. But the final position once it's inside the aneurysm is irrelevant because they don't want this situation to happen. They want the stent covering the aneurysm sac from its entire length. So predicting that very non-linear case is not useful for them. The fact that it may go there, informing them that watch out at this position, you may get a ending stent inside the aneurysm. That's important, but the final result that will be very non-linear to predict that. So we would need much more training and at the same time unneeded. So that's why we did this classification.
More questions?
Question work very much for the presentation. I have a question about a very basic feature, which is when you were talking about the rotational model, you said something about elasticity, change elasticity. But what happens if you use nitinol, which is the constitutive model such as nitinol?
Yeah, so nitinol can be implemented in that. So it's purely the material itself. So we can implement it inside that in a rotational formulation. We haven't done it yet, but yeah, we plan to do it because it just depends on the local strain on that beam.
And how do you model the friction between the wires?
So that I skipped it, but so the wires are so we don't do so we have beam to beam contact, but this is very expensive. So we have is a penalty constraint. So for this braided stents, we assume that between two wires the displacement is small. So we have a penalty constraint to limit the displacement between two nodes of two different wires.
No friction.
There is no friction. No.
Last question. Sorry.
No.
Is what about if you have it's covered by silicone? How would you model it in such a case which is common nowadays? The stem is silicone.
The wires, you mean?
Wires, yeah. So it's embedded. So
We haven't looked at that, but yeah, it would be interesting to do. But yeah, we would need to see if we can characterize the behavior of the silicon and wire altogether. So here we need to restrict to this beam model that we have. So we need to see if we can characterize that.
More questions? Everybody? Can I ask you something? When you were modeling the movement of the artery in the medium in which it is with all the other tissues, what are the assumptions of the tissue surrounding the artery? Where do you get the properties? Will it change significantly, I assume, from one patient to another?
Yeah. So it changes. So this is viscoelastic, a viscoelastic medium. It's a spring models, all distributed along the surface of the artery, and it changes. It does change within the body of one individual. It changes already. The problem is how you get it from patient to patient. That's very difficult. So we use literature data there. I mean, there are ways of estimating material properties of arteries from imaging data. I guess you could use the same to estimate those viscoelastic parameters or the behavior of the hull, let's say, but we haven't used that in this case.
Any final questions? No? Okay, well, let's thank again Miquel
Thank you.
for a very interesting